Hi there, I'm Micaela Kaplan, the ML Evangelist at HumanSignal, and this is In the Loop, the series where we help you stay in the loop with all things data science and AI. This week, we're going to explore hidden Markov models in the second part of our Markov Models series. Let's get started. If you watched part 1, you might remember that we identified 4 types of Markov models based on whether the system was observable or not and whether the system was autonomous or not. This week, we're going to dive into hidden Markov models, which are Markov models for a system that isn't fully observable and is fully autonomous. Hidden Markov models are hidden because they contain events that we can't directly observe. Parts of speech tags in a text is a common example of this. We can see the word itself, but there's no way to directly observe the part of speech. Hidden Markov models account for both these observable omissions, like the words, and their hidden causal counterparts, like the part of speech tag. HMMs, like the other models we've discussed in this series, are based on the Markov assumption. The probability of a state Qi being equal to A given a set of n states is the same as the probability of a state Qi being equal to A given just the previous state. In other words, the next state only depends on the previous state. HMMs also make a second key assumption, which we call the output independence assumption. The probability of an output, OI, given a set of n states and t outputs is the same as the probability of an output OI given just the state Qi, the state that produced it. Much like Markov chains, an HMM has a set of states, a transition probability matrix, and an initial probability distribution. Unlike Markov chains, however, an HMM includes what we call emission probabilities, or the probability that an observation OI is generated at state Qi. According to fundamental work done by Rabiner in 1989 and previous work done by Jack Ferguson in the 1960s, there are 3 fundamental problems that can characterize an HMM. The first is likelihood. Given an HMM and an observation sequence, what is the likelihood of getting the observation sequence given the HMM? We use the forward algorithm to answer this question. Number 2 is decoding. Given an observation sequence and an HMM, discover the best hidden state sequence, or, for example, given an HMM in a sentence, provide the sequence of part of speech tags. We use the Viterbi algorithm for this. The third is learning. Given an observation sequence and a set of states in the HMM, learn the HMM parameters. We use the forward-backward algorithm or the Baum-Welch algorithm for this. For all 3 types of these problems, we visualize the HMM as a trellis. Let's use a popular example from Jason Eisner in 2002 to explore this. In Eisner's problem, we want to know whether a day was hot or cold, but we don't have the weather from that day. Instead, we have a record of how many ice creams Jason ate on each day. The goal is to estimate whether a day was hot or cold based on the number of ice creams Jason ate. Let's pretend that we have the following observations: 3 ice creams, 1 ice cream, and 3 ice creams. To build our trellis, we'll start with 2 rows, 1 for each state. Then, at the bottom of each column, we put the number of ice creams that Jason ate. Each column represents 1 day of interest. On the left-hand side, before our observations, we put pi as a placeholder for the initial probabilities. Then, it's time to connect our trellis. First, we have some initial probability that we start on a hot day, and we multiply that by the probability that Jason ate 3 ice creams on a hot day. We then repeat this joint probability calculation for a cold day and 3 ice creams. Now we've connected our initial states to the trellis. Then we move to our second observation. There are 4 possible state transitions here: hot to cold, cold to hot, and cold to cold. For each of them, we calculate a joint probability, the likelihood of moving from state to state times the likelihood of eating the observed number of ice creams given the state we're moving to. We continue like this down the whole trellis. Depending on the algorithm that we're using, we'll evaluate these numbers a little bit differently. In the forward algorithm, used for likelihood estimations, we simply add together the sequence of probabilities that accumulate as we move through the trellis to get the overarching probability of a given sequence. In the Viterbi algorithm, which is used when we're looking for the best sequence of hidden states, we take the maximum of the possible probabilities at each state and use a back pointer to remember where we came from so we can compute the best path at the end. The forward-backward algorithm, or the Baum-Welch algorithm, both learn to compute the values of these matrices that we use to calculate the other probabilities. And that's it. Hidden Markov models allow us to model situations where the underlying states are not observable, but where there is an observable impact of the hidden state. From Jason's ice creams to parts of speech and more, HMMs are a powerful tool that especially impacted the early days of language modeling. That's all for this week. Thanks for staying in the loop. Want even more In the Loop? Check out our other videos. Don't forget to like and subscribe to stay in the loop.